So when we look at circuits, what are the fundamental quantities that we want to keep track of? Well, the first one of those is energy. And typically we're going to do this through thinking about the energy per charge, as in the potential. But the other one is we want to think about charge. And we're going to think about charge through thinking about the current. So what is current? In words, it's the rate of flow of charge in a wire. So what the current's telling you about is about the charge that flows past you at some point over some chunk of time. And so literally just thinking about that in terms of the amount of charge, some chunk of time will give you the average current. If a current is constant, then calculating the average current and the constant current are the same thing. Of course, if the current is not constant, then we take the limit of this as delta t approaches 0, and we end up with a derivative that tells us that the current is defined to be the derivative of the charge as a function of time. That's the instantaneous current. If we want to think about the units of current, well, obviously if it's charge per time, units of charge are coulombs, units of time are seconds, and we actually have renamed this is the ampere. The ampere is one of the fundamental units within the SI system. So how do you create a current in a wire? Well, surface charges rearrange themselves to create an electric field inside the wire. Now notice that means that this is not electrostatics, where we said in electrostatics we said that there was no electric field inside your conductor. Right? So if you have a current, you're clearly not in an electrostatic situation. And in fact, the electrons within your conductor respond to the electric field. So this is physically what goes on. For historical reasons, we actually talk about current as if it's positive charges that are being pushed through the wire. So even though in reality we know that it's negative charges, the electrons, that are moving against the electric field, we talk about current as the rate at which the electric field seems to push positive charges through the wire. Now what this does, of course, is it means that the direction of the current and the direction of the electric field, those two things now line up. Again, there's historical reasons for doing this. We sort of made this distinction before we really had an understanding of what the actual charges were that were moving. The upside is it works well. This is just the way that we choose to do it at this point. Now, of course, currents can vary both in time and in space. So obviously we've talked about, well, they vary in time just based on their definition. So if you have charge that's flowing past you faster at one instant in time and then it slows down, right, that's clearly current that's varying in time. It can also vary in space. So you'll notice here that I can also define the current as the double integral. So this is the integral over an area of this quantity J, which is known as the current density. I want the dot product of J with tiny little differential area elements. So J is the current density, it's the current per area, and basically over space, what I'm doing is saying I'm going to calculate the current by figuring out how J varies over all my little area elements and then adding that up. There's a couple ways that we can define the current density. J is equal to sigma times the electric field, and we're using sigma to stand for the conductivity. Of course, sigma, the conductivity, is related to rho, the resistivity. So the more easily a conductor conducts electricity, the less resistive it is. And so you'll see here that the conductivity is equal to 1 over the resistivity. As the conductivity becomes higher, the resistivity becomes lower. So I can rewrite J as equal to 1 over the resistivity times the electric field. Now, fundamentally, what both of these expressions are trying to tell me is electric fields produce currents. And so this is one way to think about Ohm's law. Where do currents come from? Currents come from the fact that we have charges that are located within electric fields. So as electric fields cause the charges to move, that's why we end up with currents. If you want to think about the units of J, well, again, as a current density, it's current per area. Units of current are amps, units of area are meters squared.